In this video, I want to walk you through what the stress-strain curve looks like for bone. And there's a few interesting things about it. The first of which is that the shape of that curve is going to depend on how we're loading the bone, meaning what type of mechanical loading is going into it. There's a technical term for this, and it's called, we can say that bone is anisotropic. So anisotropic, meaning it is not the same, it does not have the same, and not iso, same, tropos' response. So not the same response, meaning it depends how you load it. So for starters, let's think about what does the stress strain curve look like for compressing bone. So maybe you get tibia from a cadaver and you put it in a mechanical loading system. You're going to apply a force to it here. You're going to compress it, and you're going to study how much does it deform, with a little maybe deformation gauge or something. So there's a few interesting things about the stress strain curve. The first is that there is no toe region, meaning down here you just get a linear response right away. When we talk about cartilage and tendon, we'll talk about why those materials have a toe region and why bone does not. But the upshot right now is that bone is going to respond like a very, very stiff linear spring up until a certain point when we compress it, and then we're going to get some deformation. We'll reach the ultimate strength, and then we'll go down here, and then it breaks. So ultimate strength is up here. Here's that dividing line between the linear region, and the plastic region. Another term you'll see bandied about is something called the physiological zone, which is maybe like here. We'll just label that physiological. And that just means that in normal activities, walking and running and so on, you are staying down in this area. And you don't get up into this area, because we know that once you are up here, you are sustaining serious damage to the tissue. Now, this is for compression. Let me label that. And we could think about what would happen if we did the same experiment with the same bone, and of course, or maybe like a very similar copy of it because we broke it. But what would happen if we put tensile force into it? Like we try to pull it apart. Two interesting things happen. Number one, the bone is less stiff, so the slope is lower. The ultimate strength is lower, and then you just break much more quickly. So this suggests two things. Number one, bone is much weaker and let me label this, in tension. Much weaker in tension than it is in compression, and it is less stiff. I have over off to the side data from a real experiment showing the same thing. So this is an actual cadaver bone showing the actual straining, meaning percentage change in length. And you'll notice that in tension, right, the slope is lower and the ultimate strength is much lower. You'll notice also that it looks like the plastic region starts maybe a lot earlier. So the place where damage is going to start occurring is going to be sooner than maybe kind of roughly here for compression. So this has important consequences in how bones respond to stress. But if you think about this, it makes a lot of sense, because if we go and look at the skeleton, and I erase the things I've been drawing all evening, and we just look at what kind of loads will bones be experiencing during normal activities, it's quite clear that the long bones of the lower leg, for example, will be experiencing lots of compressive forces. You've got the body weight up here pushing down, and they're going to be compressing this bone. And there's not that many instances where the bones are going to have high tensile forces. With let me show you though one case where that turns out to be an issue. I mentioned in a previous video how a large component of the forces that the body encounters, or that the bones encounter, are actually not from your body weight, but they're from the force of muscles. So I want to consider the effects of the calf muscles coming off here. Now I know we've got the soleus, which goes off like this, and then the two heads of the gastroc, which go like this. But let's just consider them all one muscle right now. And that force is going to be, because it's coming off the calcaneus, it's going to be transmitted to the tibia. So this is going to induce a bend, we call it a bending moment, but it's going to induce bending in the tibia, meaning the tibia, this bone, is going to have a tendency to want to bend like that. Obviously, it's not this extreme, but it does occur. There's a great study that I read recently where they had one very dedicated volunteer who had pins surgically implanted temporarily into his tibia like this. And then they had him walk and run and do squats and other exercises in the lab for an afternoon. And you can actually measure the deformation, the bending of the tibia as a result of this very powerful muscular load from the calf muscles. So let me draw out that exaggerated bending, and we'll think about areas of compression and areas of tension. So while I'm doing this, think about what area of the tibia is going to be under tension, what area of the tibia is going to be under compression. So this is the tibia, and it's obviously exaggerated bending. On the back side here, we're going to see compression. And on the front side, we're going to see tension. Maybe if you imagine doing this to like a big piece of rubber or something, you can see how if you really bent this hard, it would tend to pull apart right here. And it turns out that while stress fractures from, say, too much loading in the tibia are more common on the compressive side, they are much more serious when they occur on the tension side. And the reason there is because the forces you encounter in your daily life tend to pull apart that side of the bone. It's very hard for this area to heal because it's kind of like a paper cut that you keep pulling open. The forces that you encounter, the tensile forces, pull that area apart, and bone in tension is much weaker than bone in compression anyways. So bone's a very interesting material, and its mechanical loading properties give us some very useful insights into how various types of activities will affect the loading pattern of bone. So hopefully you found that useful. I have one more video for you that we're going to touch on a topic for next week, and I'll see you in that.